Okay, so in this video today we're going to be looking at special properties of graphs, and this will finish off the curve sketching topic. So a lot of this stuff we'll start talking about is actually the knowledge from higher. So the first thing is we'll talk about inverses just very quickly. So during the higher course we met inverse functions, and we remember that the graph of the inverse function can be found by reflecting the graph of the function in the line y equals x. And the best example of that would be your f of x function could be something like an exponential function, e to the x. Therefore, your inverse function, the inverse of that was reflected, gave you log of x. Okay, so that was like the first example you seen at higher last year, or possibly the first one you've seen. But obviously, there's lots of graphs that have inverses. They get reflected on the y equals x line. Okay. However, we'll talk about some transformations just now. So a lot of transformations will also be used this year, discussed at higher. Okay, so the first one we're going to look at is the graph of k of f of x. Okay, so that's the first one there. So for example, let's say I've got a graph, very basic one, y equals x squared. Okay, that's the first one I'm doing. And let's say I want to draw what y equals 2 lots of x squared, so 2 times x squared would be. Therefore, that would multiply all the y values. Okay, I've actually not quite drawn that as well as I wanted to, so let's try that again. So it still needs to go through the origin, so let's try it again. So it would be a bit steeper line, curves down, and it would go like that there. Okay, so we've got y equals 2 of x, 2x squared there. All right. The first time you actually seen that actually would have actually been at National 5 though, and normally with your trig graphs. Okay, so the first graph we'll look at, we'll just take normal sine. Just extend my axis a little bit here to make that work. So normal sine curve, y equals sine x. That has a height of 1 and a depth of -1. Extend that as well. But if I wanted to draw y equals 2 sine x, okay, so we'd go up to 2 and -2. Still cross at the same points regarding the maximum will still be at 90 degrees along its travel. So go along there, curve back down, still cross the y-axis at 0, and back up at 360 there. So we've got the red line there being y equals 2 sine x. Okay, so that was the first time you've seen things like that at National 5. Also, there was a higher example as well there. Okay, so we've got them there. Second we'll look at is, so in this video we'll look at all graphs, so feel free to pause the video, etc. But the graph of f of x plus k, where we add some value to our f of x function. Okay, so if we start off with, again, we'll just take the basic function y equals x squared to start with. Then, okay, if we added 1 to it, therefore everything would just be pushed up a value 1. We just shift the graph upwards, okay? Now obviously we don't have to make everything go up, we can push it down. So let's say we then crossed it at -3, so it would curve like that there. That would be the curve y equals x squared -3, okay? So we translate it, we can push our graph up and down by adding a value to our function. Again, okay, you could see that with any function here. So just in general, let's say I've got a curve going a random thing, let's say it's doing something like this. Maybe not quite a sine curve, but something like that. Let's call that y equals f of x. And then if I wanted to increase it by a value k, it would just be looking the same thing. F of x plus k there. Okay, so we've got that sort of property there just in general. Alright, so there's the first two there. We'll then keep going. So what else did we see last year at higher? So last year at higher we seen we could add a value inside our bracket. So what happens when we have something like f of x plus k? Alright, so again, here we start off just with the original, we keep using y equals x squared. So what would it look like if I added k? Well, if I add k, it actually jumps to the left. That was the property that happened here. So that would be y equals x plus k all squared there. And if we minus k, it would move to the right. So therefore, that would be y equals x minus k all squared there. So we've got that property inside there. And again, we've seen that last year also regarding sine curves. So if I start off with, say, let's take the normal sine curve y equals sine x. Then we used the wave function last year a lot of times to get functions of the form sine bracket x minus, etc. Okay, so if I started with, say, for example, y equals sine x minus 90 degrees, therefore everything gets shoved to the right 90 degrees, so therefore it would start there, curve up there, go down, end up going down there, but then we need to just continue it so it looks like it's starting back on the y-axis there. Okay, so there's things that we've seen from higher as well. I've got one last one from higher before we look at anything new. The last one we looked at from higher was when we are multiplying our value k inside a bracket, so f of k of x. Okay, so we've got that there. So again, we'll use another base function. We'll call the first one x squared minus 4. So let's say I've got x squared minus 4 there. It's just the x squared graph pushed down 4, so we're crossing the 4 there. And then if I wanted to put in 2 lots of x into my function here, it would still cross at negative 4, but again it would be a steeper line. That would be 2 lots of x all squared minus 4. Okay, so I'm multiplying our x coefficient by a value, in that case 2. Alright, and again, same with sine and cos. Okay, but obviously there's a different property here regarding that. So if I again start off with the sine function, y equals sine x, and again you would have seen this at National 5. If I want to draw y equals sine 2 of x, therefore I end up getting 2 graphs in that space. Oh, not 2 at the start. Let's try that again. Y equals sine 2. So we get those properties there. So we've seen it for a lot of trig graphs. We've seen it for a lot of graphs like x squared, etc., higher parabolas, etc. Now let's look at some new properties now. Okay, so hopefully that's just a recap. Again, feel free to pause the video at any point, copy it down, look back over it, etc. But we'll now look at some new properties. So the first one we're going to look at is the graph of, and it looks like there's 2 lines before, or sorry, one before and after f of x, which stands for the modulus function. Okay, and that's not discussed at higher. You wouldn't have seen that at higher at all last year. So basically what it means is it just takes in the value of a graph. It doesn't take in the sign of a graph. So when f of x equals x, for example, f of x is negative, and if x is negative, but if f of x is the modulus of x, f takes the positive numerical value of it. Okay, so for example, if on the original graph we've got, say, a function that reaches the value negative 3, then the modulus of that, we wouldn't take the negative count, we would then change that to positive 3, we'd rate it as positive. And there's an example. So when x is negative 3, the modulus of that would be 3, always positive there. Okay. Now, the best way to treat these questions is, okay, it can always be obtained from the original graph by simply flipping any parts of the graph which appear below the x-axis, you flip them above. Okay, you're changing the sign of the y values here. And a lot of times it is better to actually draw the original graph first as well. Okay, so if I start off with the actual first function, y equals x. Okay, so the right-hand side of the y-axis is positive. That wouldn't change at all. But you can see the left-hand side of the original graph is below the y-axis, or the x-axis I should say, so therefore it would then flip and go like that there. Okay, so the right-hand side graph would be the graph y equals the modulus of x. Okay, everything would be flipped positive. Okay, just keeping the same value number-wise, but making sure anything that's negative becomes positive. Now, a better example of that would be this question here. So we want to sketch the function, the modulus of x minus 1 multiplying x minus 2. What the best thing to do is sketch the graph without the modulus first, okay? Just think about how you would sketch x minus 1, x minus 2 here. What that's telling you is that we've actually got our two roots. If you solve both of them, you get x at 1, x at 2. And if we multiplied out, x squared would be positive, so it's a minimum turning point. So I've got a parabola that's a minimum, and it goes like that there. Okay. However, what would the graph of the absolute value, or the modulus of x minus 1 multiplying x minus 2 give me? Okay. Basically, anything that's above the x-axis stays above the x-axis. Okay. So I've still got my roots at 1 and at 2. So therefore, that's going to come down, and then after that, it's still going to go up. But you can see in between my two roots, it's negative, so that means it's just going to flip upside down, it's going to go above, so it's going to curve like that there. Okay, and that's what the modulus does to a graph. Okay, it only takes in the value, not the actual sign. Okay, everything stays above the x-axis at that point there. Okay, so that's one new thing. The next thing we'll look at, and this will be the last thing in the video today, is what's known as odd and even functions. Okay, so odd and even functions, not all graphs are odd or even. However, some of them do have this property. So we'll start off with what an even function looks like. So an even function is any function whose curve has the y-axis as a line of symmetry. Curves having only even powers of x are symmetrical about the y-axis. So if I give you a quadratic, for example, which is x squared, as long as it didn't have an x term, it would be an even function. Or if I gave you a polynomial that only had x power 4, x power squared, etc., no x cubes or x powers, it would also be in that mould as well. Okay, so that's again, let's take back our first one that we spoke about today. Y equals x squared. Y equals x squared is an even function, okay? It is symmetrical about the y-axis, although my very dodgy drawing doesn't make it look like it, so I'll try that again. Because it should be turning on the origin, so let's try that again. A bit better there, a wee bit better. It's symmetrical about the y-axis, okay? The values would be identical on each side, just one positive, one negative, and we can flip it and it would get the same thing, okay? Another one would be y equals 1 over x squared. Okay, this would be a new function this year at Advanced Higher because this has an asymptote. We couldn't have x to equal 0, so the y-axis would actually act as an asymptote here. But what happens to the graph is it shoots off like that there. Okay, and you can again see the y-axis acts as a symmetrical line for that there. Those two graphs are even. Okay, now, excuse me. Sometimes though, you can actually prove a graph's even by using a separate property, so not always having to actually sketch it out. So an alternative method of defining an even function is to show that if you substitute negative x into your function, you get the same as what it would be as if it was just f of x. Okay, so again, a quick example of that would be, call this example 2. We'll do this part I. Let's say we give the function f of x equals x squared. Okay, so we know that's an even function, but how can we prove it? We can prove it by substituting negative x into it. If I substitute negative x into it, I'm going to get negative x all squared. Okay, like that there. But if I square it, we know two negatives, when we multiply each other becomes positive, I end up back with x squared. Okay, so put negative x into it didn't actually change the function whatsoever. Okay, same with the second one we looked at. Okay, so again, if I make my function 1 over x squared, then if I substitute negative x into it, then it's going to be 1 over negative x all squared at the bottom. Again, same property. that would end up becoming positive x squared. I've got back the original function. Okay, so that's an alternative way, and actually a very more systematic way to prove something is even. Okay, write down what the function is, sub negative x into it. If you get the same thing, you got started back again, you've proven the function was an even function. Okay, this leads on to then talking about what an odd function looks like. Okay, so odd function's got a bit more of a rotational symmetry property regarding it. So an odd function is a function whose curve has 180 degrees rotational symmetry about the origin. Curves having only odd powers of x have 180 degrees rotational symmetry about the origin. So if I gave you a polynomial like x cubed plus x, for example, x cubed minus 3x, all the powers of x are odd powers. They would be classed as odd functions. Okay, and the reason being, if we start off with just the basic one, y equals x cubed, if you sketch that, it would look like that there. And you can see if I spun that round 180 degrees, I would end up with the same graph back there. Okay, but again, not only do we have to sketch a graph to prove that, we can actually prove that by using this alternative method. So the difference here is, if we get given an original function f of x, say x cubed, if I sub negative x into it, we need to show we get the negative version of that function. Okay, so we'll just do that as example. We'll call example 3. So if f of x is, say, x cubed, then I substitute negative x into it. That would be negative x all cubed. If you cube a negative, it stays negative, so I get negative x cubed. So I get negative of what my original function was. Okay, so I didn't need to sketch that one. I could have done that one by proving it by subbing negative x into it and getting the negative version of what I started with. Okay, so that's actually the end of the curve sketching topic. Now there's a lot in there, so please feel back and go work through all the videos, etc. again. But regarding properties, all the stuff from higher can come up. But remembering we can now look at modulus of a graph or working out if something is odd or even as well. You okay with that?